Welcome to part 2. In part 2, we will complete item 3 and item 4, and we are almost at the end. The end is in sight. The end is in sight, right? We are like here. We are here. Great. Okay. In item 3, I will do hypothesis testing about a linear combination of parameters. This is very interesting, and I think you should take a listen and take a look. And then we will look at hypothesis testing about multiple linear restrictions, and we'll do a joint F test, and I'll help you look at the steps to do an F test. Okay, let's jump in. So here we are working on testing hypothesis about a linear combination of parameters. The example that we are using is return to education at a 2-year college and at a 4-year college. So the hypothesis of interest is whether a year at a junior college is worth a year at a university, meaning we take the beta on JC, right, and the beta on university, and we find beta 1 minus beta 2, right? And in the hypothesis in H0, we say, well, that is equal to 0, and in the alternative, we are interested to test whether a year at junior college is worth less than a year at a university. That's what we are up to. Now, the issue with doing this is the calculation of the standard error. If you look at the t-test, it's easy to just take your beta 1 hat from the regression output, your beta 2 hat from the regression output, and subtract beta 2 from beta 1 hat, right? The numerator is easy to find. It's the denominator that's difficult to find, because in the output we don't have the covariance of the two betas. And so how do we do this? Well, the remedy is, or the alternative method is, to make a substitution in variables. We can define theta 1 to be beta 1 minus beta 2, such that in the null, theta 1 equals 0, in the alternative, theta 1 is less than 0. Makes sense, right? But we have to do a change in variable, so we make beta 1 equal to theta 1 plus beta 2. So straight from this theta 1 equal beta 1 minus beta 2, I make beta 1 the subject. So I write it so that beta 1 equals to a bunch of stuff. So beta 1 equals theta 1 plus beta 2. So wherever I have a beta 1, I plug that in. And so when I do plug that in, I can write beta 0 plus beta 1 JC plus beta 2 JC plus beta 2 university plus beta 3 experience plus U. So from here, I can group, see beta 2 here and beta 2 here. Yeah, I can pull beta 2 out and have JC plus university. So that's the third line. Beta 0 plus theta 1 JC plus beta 2 JC plus university. Do you see this one? JC plus university. Because we pulled the beta 2 out. Plus beta 3 experience plus U. So now, in your statistical software, you're going to create a new variable, which is JC plus university, so that you regress log wage on JC, the new variable JC plus university, and experience. When you do that, you're going to get this output where beta 0 hat is 1.472, theta 1 hat is minus 0.0102, and on and on and on. But what have you done? Well, theta 1 hat is the difference between your beta 1 and your beta 2. So that estimate is in the numerator of your test statistic, and in the standard error, or in the denominator, you plug in that standard error we were trying to calculate before. Remember that? Yeah. And so you get negative 1.48. Now, in the p-value is 0.07, which is much greater than 0.05. You see, so here we fail to reject H naught. Now, you could do a confidence interval, and this is the 95% confidence interval. I see that because I noticed the 1.96 here. So when you do the confidence interval, but Dr. Topa, how do you know that? Yeah, look at the n. The n is super large. If we go all the way back, and pardon me to go all the way back, if we go all the way back and look at one of our T tables, do you see, right here we had degrees of freedom 1,000. Over there, in the new example that we were looking at a few seconds ago, the n was in the 6,000s. You see, so you are looking at a normal distribution here. So when we use 1.96, that's 95% confidence interval with a 5% significance level. That's how I know. Okay, let's go back. That was just a small detour to remind you of the other things that we had studied in part 1. Okay. So 1.96 times the standard error of theta 1 hat. So theta 1 hat plus or minus the critical value 1.96 times standard error of theta 1 hat. That's what we just did. And so, oh look, is there 0 in there in the interval? Yes, 0 is in the interval, and so we fail to reject H naught. And also because the p-value connected to the test statistic is greater than the p-value connected, well, it's greater than the significance level, or the p-value connected to the critical level. See part 1, please. We fail to reject H naught. Fail to reject the null. What was the null? The null was where theta 1 was equal to 0. Okay, moving along, we could do a joint test instead of multiple separate t-tests, right? Here, the null is saying that a sparse regression would have done the job, and the alternative is saying the original regression was fine. The null claims that a restricted model with the last 3 variables excluded is sufficient. The alternative says all the variables are needed in the model. And so we test that. That's the joint test. We test that how? Well, we first estimate an unrestricted model. Yeah. That's what the alternative hypothesis is saying. The alternative hypothesis is saying that an unrestricted model will do the job, that an unrestricted model is useful, right? That's what the alternative says. An unrestricted model is useful. And the null hypothesis is saying a restricted model is better. A restricted model is sufficient. Okay, so well, we estimate the unrestricted model, which the alternative favors, and we find the sum of squared as 183.186. Yes, the sum of squared residual. Good. SSR, sum of squared residual. That was fine. Now, a sum of squared residual, when you drop, variables will go up. So in the restricted model where we drop variables, the sum of squared residual will go up. Now, the increase doesn't really tell us anything. The question that we are after is whether that increase is large enough relative to the sum of squared residual in the unrestricted model to warrant rejecting the null hypothesis. And so you will notice that the f-test, that the test statistic that we'll use here is known as the f-test. The f-test in the numerator will take the difference between the restricted sum of squared regression, which grew because we dropped some variables, and the unrestricted sum of squared residual, and divide that by the unrestricted sum of squared residual, and multiply that by, what I'm saying is this, SSR minus SSR unrestricted divided by SSR unrestricted times is what I'm saying we are doing. Right, this is F. This is the F test. Then we multiply, oh, this is Q. Then we multiply by the ratio of the restrictions. The number of restrictions that we used was Q, and degrees of freedom is n minus k minus 1. So this is the relative increase of the sum of squared residuals when you go from a restricted model. When you go from an unrestricted model, that's the alternative hypothesis favors, to a restricted model, that's the null hypothesis favors, and that it follows an F distribution, that is if the null is correct. So how do we do this? Well, we take our 198.311, subtract the 183.186. Now, where is that 183.186 from? It's from here, from the unrestricted model, the sum of squared residuals. We take that difference and divide by the 183.186 and multiply it, exactly what I just did. Multiply by 347 over 3. And we find that the F test is 9.55. Now there's an F table, and people in my class can click on this link to see the F table. Others online can go into AI and look at that F table. But the F distribution looks like this. It looks like this. The rejection region is to the to the right of your 2.7. Your 2.76 is your critical F value, and the area there is your significance level, 5%, and the unshaded area is the fail to reject region, fail to reject H0 region. Yes, that F distribution is taking only positive values, right? And this is because it's connected to the sum of squared residuals. The sum of squared residuals is never negative. And so, well, what is the F test? The test statistic that we calculated, 9.55. 9.55. And what is the critical value at 0.01, at 1%? That's 3.78. You can see that your F test falls to the right of your critical value, right? In this case, that will look like this. So you have here your critical value, 3.78, and I'm going to shade that all black, and in red I will put in our 9.55. And what is the 9.55? That's the f-test, or the test statistic, the calculated test statistic. And what is the stuff in black? The stuff in black is your critical value. And the area to the right of the critical value is that significance level, in this case 1%. So you can see that our f-test falls in the reject H0 region. The unshaded region is the fail to reject region. Fail to reject H0. And the shaded region in black is the rejection region. The shaded area in black is the rejection region. Just like you saw here, right? That's the rejection region, the shaded blue area. Now, for connected to the data example, the rejection area or the reject H0 area is shaded in black. I hope that things are making sense for you. Okay, so what does this mean? This means that the three variables are jointly significant, and we should not drop them. But when we tested them when we tested them individually or separately doing the t-test, we noticed that they were separately not significant. Yes. Why? Multicollinearity could be the reason why. Multicollinearity. All right. One other thing I wanted to point out was the size, the size of the data sets, right? In the restricted model, I mean, it's going to be the same, 353, right? The size of the data set, it's not that big. It's pretty small. We just saw a data set above 6,000. This one is quite small. So potentially collecting more data could be beneficial, possibly. Can we have an overall test to test the usefulness of the model? Yes, that's the overall significance or test of overall significance of a regression model. So if we have this as our econometric model, the null will say that all the betas are 0. So none of the variables are useful in explaining our y. Basically, the null is claiming that if you would just regress y on 1, on the constant 1, then that restricted model is sufficient. The alternative says that at least one of the betas is not 0. And so we do that f-test again. This time, what are we comparing? We are comparing the explained variation in the model to the unexplained variation. And we are testing if that occurred by chance. Let's take this last example and call it a day. So we have log price regressed on log assess and log lot size and square feet and log square feet and bedrooms. Now, in this example, we are testing whether house price assessments are rational. So if house price assessments are rational, then for every percentage change in assessment, there should be an associated 1% change in prices. So that is why in the null, beta 1 equals 1 as the baseline. And all the other betas are set to 0. Meaning that all other known factors should not influence the price once the assessed value has been controlled for. So let's do that. The unrestricted regression, which the alternative hypothesis will favor, right? Because the alternative hypothesis will be against this null hypothesis. So the alternative hypothesis will favor the unrestricted regression, where all the explanatory variables are in there. Log assessed, log lot size, log square feet, and bedrooms are in there. But the restricted regression is the one where we have beta 1 equal 1. So the 1 is written here, beta 1 equal 1. So log price equals beta 0 plus 1 times log assess plus u. And so when we do, before we run that regression, you can do this where you pull your log assess across the equal to sign. So you have log price minus log assess. So you can create a new variable, log price minus log assess, as your response variable, and regress that on the constant 1, right? And then regress that on the constant 1. So that test statistic will be as we have seen it earlier, but then it's the sum of squared residuals from the restricted model minus the one from the unrestricted model, and you get a 0.661. A 0.661, well, the critical value here is 2.50, and that's the shaded region in which we reject H naught. And in red, your F test was 0.661, right? Where it falls in the fail to reject H naught region. So we failed to reject H naught in this last example. Okay, that's the end of chapter 4. We'll do more in class. For those taking my class, I will see you, I guess, next week.